In this last video for ordinary difference equations, we're going to look at the unit step function. We're going to define what a unit step, or also sometimes called as a Heaviside function, is. We're going to define the translated unit step function. We're going to write a translated unit step function for a given graph or a piecewise function. And then we're going to find the Laplace transform for a step function. So let us look at what a piecewise continuous function would look like. We're going to define the unit step function at t equals 0, also called the Heaviside function, as u of t is equal to 0 if t is less than 0 and equal to 1 if t is greater than 0. The translated unit step function u of t minus c can be used to provide a jump at an arbitrary point where t is equal to c for any real number c. Another definition we have, definition 6.6, a unit step function at t is equal to c for an arbitrary real number c is defined as this. U of t minus c, 0 if t is less than 0, 1 if t is greater than 0, and you can see that we are down here at 0 for t less than 0, and at some arbitrary c that it jumps up to 1. The notation u sub c, which is equal to u, when I see u sub c, this is the same thing as u of t minus c, which you may see it as with an h, meaning the Heaviside, t minus c. As an example, if c was 5, then the notation would be u of sub 5, or u of t minus 5, or h, capital H, of t minus 5. We can think of a Heaviside function as a switch that is off until we reach some c value, when t is equal to that c value, at which point we'll turn on and it will take on that value of 1. Heaviside functions can only take on zeros and ones, but we can use them to get other kinds of switches and other kinds of values, such as u for u sub c of t is switched off until we get to that arbitrary t, and then when it turns on, it's going to take on a value of 4 because 4 is a multiplier. Likewise, negative 7 u sub c of t will be switched off, but when it turns on, it will take on a value of negative 7. So now we can write a piecewise continuous function as the sum of continuous functions, each multiplied by the appropriate unit step function, and an arbitrary piecewise continuous function with n number of jumps and continuous between the jumps can be defined like this. So f of t is equal to f sub 1 of t if we have from 0 to t to some t sub 1, f sub 2 of t if it's from t sub 1 to t sub 2, and etc. You might also see it wrote in this manner. F of t is equal to f sub 1 of t plus u of t minus t1 f sub 2 of t minus f of t sub 1 plus u of t minus 2 f sub 3 of t minus f sub 2 of t, all the way up to u of t minus t sub 1 f of n of t minus the previous f of n minus 1t. If I'm asked to write a switch function or a Heaviside function of this, I'm just going to follow this pattern. So, first thing is f of 1. F of 1 is negative 4. So I can write this f of t is equal to negative 4 plus. I have u of t minus t sub 1. This is t sub 1. So this will be u of t minus t sub 1, which is 6. And then I'm going to do f of t sub 2 minus f of t sub 1. So then I'm going to do 8 minus, or excuse me, it's going to be 25, that's f of t sub 2, minus 4. So 25 minus a negative 4. And then I'm going to do my u of t minus 2, so plus u of t minus, and this is my t sub 2, so minus 8. And then it's going to be f of 3 minus f of 2. F of 3 is 16 minus f of t sub 2, which is 25. And then I have my last one, which I'll do in yellow. So my last one is plus u of t, and it would be t minus here, which would be t minus 3. So that's 10. And then it's going to be multiplied by 10 minus 16. So this f of t can be rewrote as negative 4 plus 16 minus the 25. Excuse me, the 25 minus a minus 4 is 29. U of t minus 6. And then plus, actually it'll be a minus, because it will be 16 minus 25, which is negative 9. U of t minus 8. And then my last one is going to be another negative. So 10 minus 16 is negative 6. U of t minus 10. Well, that should be 30. T minus 30. So let me change that. That should be t minus 30. So this is 30, and this is 30. And I'll show you why it should be 30. Because that is my t sub 3. That is my t sub 3. So it is 30. So that should be 30. I hated it when my professors would arbitrarily erase and not explain why and where it happened. This is why and where it happened. Now, I'm asked to find a Heaviside function for this given graph. So the first thing I'm going to do is figure out where I break up. Well, I break up the first time at pi over 2. I break up again at pi, and then that's it. So I'm going to write a piecewise function that describes this graph. So I'm going to have this equal to, now the first piece is the cosine of t. So here's my first piece. It will be the cosine of t if I go between 0 and pi halves. And then I have this output, which is 1. So it's 1 when we run between pi halves and pi. And then here's my last one. And this is negative 3 if pi is less than t. So once I have wrote it as a piecewise function, I'm now going to write it in the appropriate Heaviside or unit step function. So I have f of t is equal to, so I have my first f sub 1, which is the cosine of t, so cosine of t. And then plus u of, it'll be t minus my t sub 1, which is pi halves. And then it's going to be 1 minus the cosine of t. Now this time I have a function instead of a numeric value, and that's okay. Then plus u of t minus pi, and then it's going to be negative 3 minus negative 1. So cleaning this up, I get the cosine of t plus u of t minus pi halves, 1 minus the cosine of t, and then minus 4 u t minus pi. Okay, so now that we have done a couple of these piecewise functions and wrote them as Heaviside or unit step functions, we can now use Laplace transforms on these step functions when we use these following theorems. My first theorem is the Laplace transform of a unit step function of u of t minus c for any c greater than or equal to 0 can be rewrote as e raised to the negative cs over s. Also, the Laplace transform of u of t minus c and then some function of t minus c can be rewrote as e raised to the negative cs of capital F of s, where capital F of s is the Laplace transform of that f of t. And lastly, we have the Laplace transform of u of t minus c f of t is equal to the Laplace transform of u of t minus c g of t minus c. Notice how I went from f of t to t, some other function of t minus c, so that we can go from there to e raised to the negative cs of cap g of s. So we have these Laplace transforms and we extend the table. So find the Laplace transform for the following function. Well, the first thing we're going to do is notice this subscript u of 12, u of 6, and u of 4. So let's rewrite this as g of t is equal to 10. Now remember, the u of 12 would be the same thing as u of t minus 12, plus 2 t minus 6. U of, and the u of 6 here is going to be t minus 6. Then minus 7 minus e raised to the 13 minus 3t u of t minus 4. And don't drop the cube on the t minus 6. One other thing to note is that this has to match up. The f of t minus c, and I put 3, t minus c must match up the u of t minus c. This doesn't quite match that up. So what I'm going to do is I'm going to rewrite this as 7 minus e. If I factor out, because it's t minus 4, if I factor out a negative 3, then I would have a t minus 4. So I'm going to rewrite this as negative 7 u of t minus 4, and then plus e raised to the negative 3 t minus 4 u of t minus 4. All right, now I think I'm ready to do the Laplace transform, give or take. Now, this is kind of a little sticky, but this is of the form, this is like t raised to the n, where n is equal to 3. So when I do the Laplace transform, I'm going to use the t to the third type form for that Laplace transform. Okay, so now I'm ready to do the Laplace transform. So when I do the Laplace transform, I'm going to get capital G of s, capital G of s. Now that 10's just coming along for the ride, and then the u of t minus 12 is going to follow this one up here. So this is going to be e raised to the negative 12s over s. That's this first one. The second one is going to be 2. It's going to come along for the ride. And I'm going to use the n is equal to 3 of t to the n type form. That is then going to be multiplied by 3 factorial over t to the 4th. Because I have u, e to this, so I'm going to look at this one. So this is going to be then multiplied by e raised to the negative 6s. My last one, because I broke it apart, that's this one right here, because I broke it apart, the first part is just going to be like the 10 u of t to the minus 12. So this is going to be minus 7 e raised to the negative 4s over s. And then now that this matches, I can use the Laplace transform using this type of Laplace transform, this one right here. And then it will become, so minus 1 over s plus 3 because of this. That's what that part comes from. And then the u of t is just going to be e raised to the negative 4 of s. And that should be a plus. And that's it. Let's take a look at my next example here with b. So the first thing we're going to do is write it out appropriately. So g of t is going to be u of t minus 1 plus te raised to the negative 3t u and then t minus 4. Now t, some side notes, t is the same thing as t minus 4 plus 4. You're thinking, why am I doing that? Well, because remember, it must be t minus that same c, and I only have t, not t minus 4. So that t can be rewrote as t minus 4 plus 4, okay? And then my e raised to the negative 3t. Well, I'm going to rewrite this because remember, it has to be of this t minus 4. So negative 3 t minus 4. That should be an e. But I can't just arbitrarily just say, hey, I'm just going to go ahead and do this minus 4 there. So if I were to distribute that negative 3, I would actually be adding 12, so then I have to subtract off 12. So I'm going to rewrite this as e raised to the negative 3 t minus 4, and then e raised to the negative 12. So then this is the same thing as u of t minus 1 plus t minus 4 plus 4, e raised to the negative 3 t minus 4, e raised to the negative 12, u of t, u of t minus 4. And now I'm just going to rewrite it just a little bit more. Let me just erase this. And so I'm going to rewrite this as u of t minus 1. That's cool. I'm going to distribute the, actually, that's not a parenthesis, that should be a plus. I'm going to distribute, but first I'm going to write e raised to the negative 12 out front because that's just a numeric value. So that's going to be just a multiplier. And then I'm going to have e, I'm going to have t minus 4 multiplied by e raised to the negative 3 t minus 4. And then I'm going to have plus 4e raised to the negative 3 t minus 4 multiplied by u of t minus 4. Rewrite this one more time. So I have e raised to the negative 12. T minus 4, e raised to the negative 3, t minus 4, multiplied by u of t minus 4. Plus e raised to the negative 12, multiplied by 4, multiplied by e raised to the negative 3, t minus 4, u of t minus 4. All right, now I'm ready to do my Laplace transform. So doing my Laplace transform, I get capital G of S is equal to e raised to the negative s over s. That's just this part. Plus e raised to the negative 12. When I do the Laplace transform of t minus 4 e raised to the negative 3 t minus 4, this will become 1 over the s plus 3, the quantity squared, e raised to the negative 4s, plus e raised to the negative 12, and then we have a 4 as a multiplier, so we'll do a 4 out front here. And then it'll be multiplied by 1 over s plus 3, e raised to the negative 4s. And that's it. Now, let's take a look at C. So the first thing we're going to do is rewrite this as y prime plus 3 of y of t is equal to. I'm going to use the Heaviside or unit step function. It will be my first f of 1, so 0, plus u of t minus 2, 9 minus 0, plus, and then it'll be u of t minus 5, and then 0 minus 9, 0 minus 9, and then that's it. Okay, so this is going to be u of t minus 2 multiplied by 9. Oh, that's nice. And then minus 9 u of t minus 5. Now I'm going to do the Laplace transform. When I do the Laplace transform of y prime, this is going to be s cap y of s minus my initial value, which my initial value of y is 9, plus, now this part is going to be cap y of s, so 3 times cap y of s. And then on the other side, I'm going to get 9 as a multiplier, e raised to the negative 2s divided by s, minus 9 as a multiplier, e raised to the negative 5s divided by s. So solving for cap y, so cap y of s, so I would move this 9 to the other side, and then I would factor out of the y, cap y of s, s plus 3. So I would have factored out a s plus 3. On the other side, I would have moved 9 to the other side, and so I would have had 9e raised to the 2s minus 9e raised to the negative 5s plus 9s, all divided by s. And then I would divide everything by s plus 3, and so I have cap y of s is equal to 9e raised to the negative 2s minus 9e raised to the negative 5s plus 9s, all divided by s plus 3. Now, if I wanted to solve for this system, then I would do my partial fraction decomposition as usual. I would have said 9e raised to the negative 2s minus 9e raised to the negative 5s plus 9s all over s plus 3 is equal to a over s plus b over s plus 3. And then I would have done my usual partial fraction decomposition. And if we ignore the e raised to the negative cs to do this, what we would end up with, our final answer is y of t is equal to 3u of t minus 2 minus 3u of t minus 2, e raised to the negative 3, t minus 2, minus 3u t minus 5 plus 3u of t minus 5, almost done here, e raised to the negative 3, t minus 5, plus 9e raised to the negative 3t. And that would have been my cap y, or excuse me, not cap, this is my lowercase, this is my solution, y of t. And there it is. And that's it for this video. That's it for this class. And we'll talk about this more in depth in class.